In part 2 of the buck converter analysis, we'll be looking at the various waveforms of a buck converter, which will give us a much clearer understanding of the operation of a buck converter. We will use these waveforms to come up with expressions for the high frequency ripple in the inductor current and in the capacitor voltage, and this will eventually lead us to the design methods for the different components of a buck converter, which we will be taking up in a different video. Here is the schematic of the buck converter with the various voltage polarities and the current directions defined in the schematic, and below the schematic are the equivalent circuits valid separately in the on interval and in the off interval. So this is something that we studied in a previous video, but essentially during the on interval the switch is on, S1 is on, therefore the switch is a short, and we also established that when S1 is on, D is open, and that is this open circuit here. Then you have the LC filter and the load, and during the off interval S1 is off, therefore it is open circuited, and simultaneously the inductor current forces the diode to conduct, therefore the diode is a short circuit. Now for a given operating condition and for a given duty ratio, this is how the drive signal Q sub A looks like. Essentially when Q is 1, the switch is on, and this period is D times TS interval, and when Q is 1, the interval is 1 minus D times TS duration. Now we will be assuming an operating condition called CCM, which stands for continuous current mode of operation, and for much of the analysis initially we will be assuming CCM. This essentially means that the inductor current is continuous and it is above 0 for all operating conditions. Later on we will be introducing the other mode of operation called the discontinuous mode of operation, or DCM, but let's focus on CCM for the present. Now in CCM, the pole output voltage V sub A, we have seen this waveform before also, so this is equal to, when Q is 1, V sub A is Vn, assuming ideal switch, and when Q is 0 and assuming an ideal diode with no forward drop, V sub A is 0. Now from the equivalent circuits we can see that both in the on interval and the off interval the circuit is really a second order circuit, LC circuit. So therefore to analyze this circuit and to draw the various waveforms like the inductor voltage or the inductor current or the capacitor voltage, even in steady state, we would really need to solve a second order differential equation, which can be done, but it is it's more complicated than necessary, and also it does not give us a very intuitive feel for the operation of the buck converter. So instead what we will be using is this concept of small ripple approximation that we studied in a previous video, which essentially says that for different for the purpose of different analysis, we will be assuming that the if you bring up the pen, so essentially we'll be assuming that the instantaneous capacitor voltage, which is this voltage here, is equal to the its DC value. Okay. Now we know that this has high frequency ripple, but all we are saying here is that that high frequency content is negligible in comparison to the DC component. Now this makes the analysis simple for certain waveforms. Certainly we cannot use this equation when we are trying to draw for example the capacitor current, or if we are trying to design the capacitance, then we do that based on limiting the high frequency content to a small value. For that purpose we cannot use this small ripple approximation. But for say drawing the inductor voltage and therefore the inductor current, this is certainly can be used, and it will greatly simplify the analysis. Let's use this small ripple approximation first to draw the inductor voltage waveform V sub L. So during the on interval we can use the first equivalent circuit shown here. We want V sub L. So the one end, the left end is connected to Vn, so this end is Vn, and the other end, so this is the VO voltage, and here is where we apply the small ripple approximation. So we essentially say that the capacitor voltage as shown here is a constant of value V sub O. So therefore VL is a constant DC voltage of magnitude V in minus VO. Now and this lasts for the duration of D times TS, and when the switch is turned off, then we go to this equivalent circuit for the off interval. Again, in this interval, if you look at VL waveform, the left hand end is shorted to ground, so it is 0, and the other end is still VO, therefore VL is negative VO as shown here, and this lasts for the duration of 1 minus D times TS, and then the cycle repeats exactly if this is in steady state. And we see that in steady state the VL average has to be 0 as indicated here, or the positive area should be exactly equal to the negative, or the area under the negative part of the waveform, so that the VL average is 0. Now this is a very typical waveform for inductive voltage in almost all DC to DC converters. That is, they have constant magnitudes during the on interval and a different constant magnitude during the off interval, and such that their average is exactly equal to 0 in steady state. Also notice how easily we were able to draw this inductor voltage waveform without having to solve two separate second order differential equations, one for the on interval and one for the off interval, and taking care to note down the start and end voltages of the two states of the converter. So that is the advantage of using small ripple approximation and this type of analysis. Now that we have drawn the VL waveform, we can also use that and use this volt-second balance principle across the inductor once again to show the input-output relationship, which we did derive earlier, but this will be sort of a check. And in some converters, maybe it is easier to use volt-second balance principle to derive the input-output relationship. So volt-second balance essentially means that VL average is 0. So look at the voltage during the on interval, it is V in minus VO, and the duration is D times TS. And during the off interval, the magnitude is negative VO, that is this part, and the duration is 1 minus D times TS. And this whole thing divided by TS is the average, and that should be equal to 0. So cancel the TS's, and what we have is VO times D, Vn times D equals VO, or as we derived earlier, VO over Vn is exactly equal to the duty ratio. Next, we will use the inductor voltage waveform that we derived earlier to draw the inductor current waveform. So the voltage current relationship for an inductor is as shown here. IL of t equals IL at a starting time TO plus the integral of the inductor voltage from TO to T. Here the small ripple approximation makes it easier to draw the waveform of the inductor current because essentially the inductor voltage is made to be a constant during the on interval and during the off interval as well. Therefore, the inductor current waveform would be linearly rising and falling waveforms, essentially a triangular wave shape. So for example, during the on interval, the voltage is a constant V in minus VO. Therefore, the inductor current would be linearly rising with a slope given by this expression. So essentially L di over dt equals the inductor voltage divided VL, or if you want the slope or the di over dt, then take the L here, so it's VL over L. So inductor voltage divided by the inductance is the slope of the waveform, and during the on interval it happens to be M1 is the slope in the on interval, so that is the inductor voltage, which is V in minus VO divided by L. Similarly, if you look at the off interval, then the inductor voltage is another constant, it's negative VO. Therefore the slope would be negative, or the inductor current waveform would be linearly falling, and the slope is once again VL over L, so which is minus VO over L. So using these two points, we can draw the waveform of the inductor current as shown here. So during the on interval, the slope is as shown here, Vn minus V over L, and during the off interval, it is a negative slope equal to minus VO over L. But it is important to note that this is not unique. This is not the only possible waveform for the inductor current. The wave shape is decided by the wave shape is unique. It is rising at this slope, it's falling at this slope, so that is unique. But depending on the starting value of the inductor current at the start of the cycle, we can have many different curves, a family of inductor current waveforms. For example, this is also a possible waveform for the inductor current. So is this, starting from 0, going up with the same slope, coming down with the same slope. In fact, it can also be negative, but will be rising during the on interval and falling during the off interval. All of these are valid waveforms. So from this family of curves, what is the correct inductor current waveform? It depends on the starting value, which we will obtain using some other principles, which is we will determine the average value of this inductor current. So essentially, given this voltage waveform for the inductor, there is a family of curves possible for the inductor current, and we will use the correct one will be the waveform which has the average value that we obtain from the circuit operating conditions. So essentially, we can get the average current by doing a KCL at this node in an average sense. So so remember that the KCL and KVL, they are valid in an CCA average sense as well. So writing KCL at this node is essentially IL average is equal to IC average plus IO average, as written here. IL average equals IO plus the IC average. But since we are analyzing in steady state, the capacitor current average has to be 0, or IC bar here is 0. Therefore, IL bar, average inductor current, is exactly equal to the load current IO as shown here. And once again, from our small ripple approximation, if VO has negligible ripple, so does IO for this resistive load. Therefore, IO is a constant DC. Okay. So essentially, from the family of curves that I talked about for the inductor current possible waveforms, the one which has the average value equal to the load current is the correct unique waveform for the given operating conditions, and that is indicated by this red waveform, red line in the inductor current waveform. So that is IL bar, and that is equal to IO. The next waveform that we will be analyzing is that of the current through the output capacitance IC. We want the instantaneous current. We know that the average of this current is 0, but we want to draw the instantaneous current through the capacitance. To obtain this waveform, we can use the KCL again at the same output node, but in this case KCL in an instantaneous sense. So therefore IC instantaneously is equal to IL minus IO from KCL at this node, or as shown here, IC of t is IL of t instantaneous minus the load current. So essentially, this is the IL waveform, and the IO is this average value. So just remove the DC component of this waveform IL, we get the capacitor current waveform, so which is shown here, obtained essentially by the method that I described. Remove the DC component in IL. So at this instant of time, IL is IO minus a small ripple component, and that is what is shown here, and so on. So once again, you can notice that this is where, even though by small ripple approximation we say that the capacitor voltage is close to being a constant DC, it really is not. There is a small high frequency component in the voltage, and that high frequency component was really created by this small high frequency ripple in the capacitor current. And of course the average value of the capacitor current has to be equal to 0, and that is indicated by this red line for the capacitor average current value. The last waveform in this slide is the input current for the buck converter, current drawn by the buck converter from this DC voltage source, which is also, as seen from the schematic, equal to the switch current. So when the switch is on, the current drawn from the input, or IN, I should have defined it here, IN is in this direction, IN instantaneous. So IN is exactly same as the inductor current when the switch is on, because the diode is off at that interval. And when the switch is off, that is during this 1 minus d times Ts period, you can see that there is no current drawn from the input source. So therefore IN during the off interval is 0 as shown here. So it's same as inductor current during the on interval, and it is 0 during the off interval. Next, let's look at the average value of the input current. So essentially I want to derive what is this IN bar or IN average, and we can do this essentially in two different ways. The first one is to apply the definition of cycle by cycle averaging. That is to say, take the average of IN, instantaneous IN, over one complete switching period, or obtain the area under this curve, divide by Ts to get IN average. Now I think we have not defined this quantity delta I over 2. So essentially the inductor current has this this waveform, a piecewise linear waveform, and this peak-to-peak variation, from the lowest point to the highest point, that is what we define as delta I or delta IL. And since the input current waveform IN is exactly same as the inductor current during the on interval, the input current also rises from, and we also know that for the inductor current its average value was IO. So this part is IO minus this delta I over 2, and this peak point is IO plus delta I over 2 as indicated here. So the average or the area under this trapezoidal portion would be the sum of these two, which is essentially 2 times IO, because the delta I over 2 they cancel, divided by 2 times this duration, which is d times Ts, and there is nothing added during this off interval. So this is the total area divided by Ts, gives you d times IO. So that is the average input current. This is nothing but the duty ratio times the output current. Okay, and that is indicated by this steady line. This is the CCA value of the input current, and that is equal to d times IO. Now we can also obtain the input current average value using another principle that we studied earlier called the power balance principle, which essentially says that the in steady state and in an CCA average sense, the input power, the average input power, is equal to the average output power, assuming there are no losses in the system. The average PN is the average of the product of Vn and In, and since Vn is a constant DC, that is indicated here, so Pn average is simply this constant Vn times the average input current In bar. That is equal to the output power, and the output power is the VO times IO, both steady DC values. Okay. So from this equation you can see that In bar is VO times IO divided by Vn. And we already know that this quantity VO over IO, the input-output relationship for a buck converter is VO over Vn equals D. So therefore this quantity is D, or In average is D times IO, which is essentially the same result that we derived from the other method as well. Now this is an important concept. We can use this effectively to obtain different average values, most importantly average input current values. So So another way of writing the power balance is simply to say that VO over Vin, which we derive, which is the first thing that we derive for most converters. So this is exactly equal to In over IO. Notice the reversal in the input output. So VO times IO equals Vin times In. That's where this comes from. Okay. And for a buck converter, this is equal to D. So finally, I should also mention that as seen from this waveform, the input current is really a pulsating current waveform. This is switching current, switches at high frequency, at the switching frequency. And for many applications, we would also need an input side filter, an input LC filter, such that the final current drawn directly from the input DC source is pure steady DC current. Now, having seen the various waveforms, we are now in a position to apply these to quantify the high frequency content in the inductor current, and in the next slide in the capacitor voltage waveforms as well. So we will make use of the inductor voltage and in the inductor current waveform to come up with this expression for the peak-to-peak value of what we call as a high frequency ripple. So essentially delta IL is defined as the difference between this peak point and either the starting value or the ending value of the inductor current. Now in steady state, the start value and end value by definition have to be equal. So therefore delta IL is from this peak to either the start or to the end. So we will make use of the basic L dA over dt equals VL expression, and we can use either the on interval or the off interval to calculate this peak-to-peak ripple value. I should also define the intervals. This on interval is the d times ds duration, and the off interval is 1 minus d times ds duration. Okay. So let's first consider the on interval. We'll also do the analysis using the off interval and show that they give identical results. So during the on interval, if we substitute the correct quantities in this expression, this is L, and di, the total change, is by definition delta IL, so that is shown here, and dt, the change in time, is the total duration of this interval, which is d, duty ratio d times ds, and that is equal to the inductor voltage during that interval, which is a constant, equal to Vn minus Vo. And recall that Vn for a buck converter is equal to Vo over d, that is Vn, and therefore this expression simplifies to Vo times 1 over d minus 1, or Vo times 1 minus d over d. So therefore we obtain the expression that we are looking for the peak-to-peak value of this ripple current delta IL, and that is equal to Vo times 1 minus d. Well, I'm also going to cancel this d with this d here. Therefore delta IL is Vo times 1 minus d times this ds divided by L. So that is the total peak-to-peak ripple in the inductor current. In one of the future videos, we'll be using this expression to come up with the design method for this value of inductance. And if we consider the off interval, then again substituting the correct quantities in this expression, here is L as it is, the total change in the current again by definition is delta IL, and this duration is 1 minus d times ds, as shown here. And during this period, in the inductor voltage, at least the magnitude, is Vo, and that comes here. Therefore delta IL, probably I should write it as delta IL. So once again, delta IL is equal to Vo times 1 minus d ts, this goes here, divided by this L, okay, which is essentially exactly the same expression that we obtained in the analysis for T on interval. In this slide, we are going to derive an expression for the peak-to-peak high frequency ripple in the capacitor voltage. Now I should note an important point here. In this slide and in this video, we are going to focus only on the on an ideal capacitor. So that is, the expression for the ripple that we derive here is based only on the capacitive impedance. Now later we will see that the ripple is dominated by the equivalent series resistance of the capacitor. But for now, in this slide, in this video, we're going to focus only on the ideal capacitor. So the waveform shown here correspond to the capacitor current in the top plot and the capacitor voltage in the bottom plot. And from the input-output relationship, which is essentially C dV over dt is the capacitor current, we know that the capacitor voltage is really the integral of the capacitor current, and the capacitor current itself is this triangular waveform. Essentially, the inductor current minus its own average value is the capacitor current. The main point to note here is the capacitor voltage rises when the capacitor current is positive. So that is, starting from this point, when the capacitor current is 0 and rising, the capacitor current beyond this point is positive. This entire duration it remains positive. Therefore, during that period, within these two lines, the capacitor current is positive. Therefore, the voltage is increasing. The rate at which it increases depends on the magnitude of the current. Now, this total change in the capacitor voltage is what we call as the delta V naught, or the peak-to-peak ripple in the capacitor voltage. And again, as seen from the waveforms, beyond this point, the capacitor current is negative. Therefore, the voltage begins to drop. So the capacitor voltage itself has a large DC component. For example, in this waveform, this part is 5 volts, and so this division, this point here is 5.005 volts. So just 5 millivolts change here, or roughly a total of looks like about a 12 millivolts change in the capacitor voltage. And we are trying to derive an expression for this delta V naught based on the operating conditions. Okay, so once again, this is the capacitor current waveform, and the area under, we could consider either the positive portion of the current waveform or the negative portion of the current waveform. Both give identical, they have identical wave shape, and they obviously give identical results. So let's consider the positive portion of the waveform. Essentially, the area under this positive portion, that is the one that causes the delta V naught. The integral of the current, or essentially the charge, causes this voltage dV voltage increase, or delta V naught is really the delta Q, which is this area under the current waveform, over C, or the integral IC during that period divided by C. Now I have written this duration as Ts over 2. Now this is true for any value of duty ratio because of this linear waveform for the capacitor current. So essentially, the duration from here, from the starting point up to this point here, that is the dTs period. So this whole thing is d times Ts, and this part, so during this period the current goes from the negative peak to the positive peak. So exactly at 1/2 of dTs it is equal to 0. So therefore the remaining period from here to the peak is dTs over 2. And from a similar analysis, the duration from this point to this point, that will be 1 minus d times Ts, and from here to the end of the point that we are considering, that is equal to 1/2 of 1 minus dTs, which is 1 minus dTs over 2. And if you add these two, obviously you get Ts over 2. So it's really Ts over 2 times d plus 1 minus d. So they cancel, you get Ts over 2. So regardless of the value of the duty ratio, this duration is always Ts over 2. And we want the area under the triangle, so that is equal to so 1/2 times the this magnitude, which is delta IL over 2. Again, the current in the capacitor is really just the ripple part of the inductor current. The peak-to-peak ripple in the inductor current is delta IL over 2. So that is from this negative to this positive is delta IL. Therefore, from 0 to the positive peak is delta IL over 2, and that is what is shown here. And the duration, which we just established, is equal to Ts over 2, and divided by C, we get delta VO. Okay. So delta VO is delta IL, the inductor current peak-to-peak ripple, divided by 8 times C, and this Ts has been written as 1 over Fs, and that comes here in the denominator. So that is the final expression for delta V naught. And again, I repeat myself, the presence of non-idealities in the capacitors, especially the equivalent series resistance, significantly changes the capacitor ripple shape as well as the magnitude, and that is something that we will be taking up in a different video when we look at how to design a capacitor for a given peak-to-peak ripple voltage specification.